So I thought I'd send you a little bit more about energy. You know how to calculate the quantity of energy released in a calorimeter. Q equals MC delta T. You know that when you make a solution, you can calculate that quantity of energy. And you know that this graph right here in front of you is the graph that we use to look at how energy is involved in a chemical reaction. So you do need to be very comfortable and familiar with this graph and all the parts of it. So can you label the parts of this graph? All right, so let's take a look. How did you do? Hopefully you were thinking the reactants over here on the left. We can see the amount of energy those reactants have. At the top, the activated complex, and at the end, the products and the energy of those products. Keep in mind, hopefully you were thinking this is an endothermic reaction. If we start with our reactants down here and thinking about them as a ball rolling on the hill, we have to push those reactants up that hill, that energy hill, to get the amount of energy. And then our products have much more energy. So that's why it's endothermic, taking in energy. So hopefully you did good on that. Now, as you know, those calorimeters can be used in chemical reactions. When we made the solution the other day, that wasn't a chemical reaction, it was just a physical change. But here is a chemical reaction for you. Now, how are we going to attack a problem like this? Well, hopefully you were thinking we've got to write the equation. Now, what do I got to do with this equation? Of course, I've got to balance it. And then what we're going to do is we're going to notice that in this equation, only calls for 1 mole of methane. When it burns 1 mole of methane, this is our energy that is released. But in this situation, we were only going to burn 5.8 grams. And so we're going to have to calculate that 5.8 grams. Now, keep in mind that as we're doing this reaction, the energy is negative because heat energy is releasing. This is an exothermic reaction. All right? And so hopefully you would say, well, first we've got to convert those grams to moles. Once we know moles of methane, so we're not even using 1 mole of methane as our recipe called for, we're only using 0.3625. And so we're going to compare that to the equation where 1 mole of methane is burned and it releases 890 kilojoules. And so the amount of energy that's going to be involved in this reaction when we're only burning 5.8 grams is 320 kilojoules, rounded to 2 significant figures. All right, let's take a look at another problem. This might be something like you're asked to do, and you'll be given the equation. Now, I would suggest you pause the video and see how you can do with this problem. All right, how did you do? Hopefully you first converted those grams of hydrogen peroxide to moles of hydrogen peroxide. Then because this equation calls for 2 moles of hydrogen peroxide to release 190 kilojoules of energy. Hopefully you went straight across the top and multiplied those. So 22.4 times negative 190 divided by 68. And hopefully you came up with 62.58. That's what I come up with. So I would round that, and that's again kilojoules. So I would round that to 62.6, getting rid of that 5.8 and just make that a 6 for 3 significant figures. I hope this helps you. These are the kind of problems that you'll do in this week's review quiz and on Active Chem. If you have any questions, please feel free to let me know. Bye now.